Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video on determinants. So what is a determinant? Well, it's a number that we give a square matrix, so we're only interested in square matrices here, and that number indicates the scaling factor of n-dimensional physical quantities. So you're probably saying to yourself, what the hell does that mean? Well, let's look at an example to show you what it means. Let's look at the matrix A. So this is a square matrix, it's 2 by 2. So it turns out that the determinant of this matrix is 2. So don't worry if you don't know yet why that is, because I will explain it later in the video. So we're looking now at 2 dimensions. So the determinant of A being 2 means it scales areas by 2 when the linear transformation is applied. So let's look at an example of this. So we're in R2, Cartesian plane, real numbers in 2 dimensions. So let's look at a square that has vertices 0, 0, 0, 1, 1, 0, and 1, 1. So this square here, unsurprisingly, if I call it S, has area 1 unit squared, okay? So that's easy. You knew that since primary school. But now what I want to do is investigate the effect of the linear transformation induced by A on this square. So what I'm going to do is I'm going to apply matrix A, the linear transformation, to each of the vertices of this square. So to apply the linear transformation to each of the vertices of the black square, I just write each vertex as a vector, and then I multiply A by that vector. So if I multiply A by 0, 0, I just get the 0 vector again, unsurprising. If I multiply it by 1, 0, I end up getting the vector 2, 0. So again, this is just normal matrix vector multiplication. So this one goes to the vector 3, 1, and the last one goes to 5, 1. So let's have a look at what the new shape will look like with these 4 vertices. So 0, 0 stays where it is. 1, 0 goes from here over to here. And then 0, 1 goes to the point 3, 1. And then the last one goes to 5, 1. So if I plot all the vertices and join them up, I get this shape here in green. So it's no longer a square because the linear transformation has sort of stretched it, it's rotated some points, and so on. So it turns out that this shape is a parallelogram. I know that because I can easily use Pythagoras and I can find the lengths of each side. Now, because opposite sides are equal, it's a parallelogram. So what would its area be? Well, let's call this S dash, so the image of S. So the area of a parallelogram is base, which here is 2, times perpendicular height. And the perpendicular height here is just 1, because it's gone up 1. So the area of S dash is just 2 times 1, which is 2 units squared. So what's happened is we started with a shape with area 1, and we applied the linear transformation A. And that gave us a shape that's area is now 2. So the area has been doubled, multiplied by 2, and that's because the determinant of A is 2. If the determinant of A was 3, then the area of the image shape, S dash, would be 3. The area would triple. So that's what the determinant means. Whatever area you started with, you times it by the determinant of the linear transformation matrix, and that will be the area of a shape in the image. So it wouldn't have mattered whether I started with a square or a rectangle or even a circle. If I apply the linear transformation to the points that enclose the shape, its area will be multiplied by the determinant of the linear transformation matrix, in this case 2. Now, some matrices actually have a determinant of 0. So what does that mean? Well, let's look at an example of that. So let's look at this matrix B, which has elements -1, -4, 3, and 12. So it turns out that the determinant of B is equal to 0. So what does that mean in terms of areas? We're talking areas again because B is a 2 by 2 matrix and the two-dimensional physical quantity is area. So this reason that the determinant 0 is because of something we've learned before about linear independence. It turns out that the columns of B are not linearly independent. They are linearly dependent. And we can see that straight away because the second column is a scalar multiple of the first. The second column of B is just 4 times the first column of B. So we've also learned in previous lessons that when the columns of the matrix are not linearly independent, when they are linearly dependent, that means that the columns don't span the full dimension. So in this case, B is a 2 by 2 matrix. Because it only has one linearly independent column, its columns, see them as vectors, they span only one dimension. One dimension because there was one linearly independent vector. So if we take our matrix B and let's multiply it by an arbitrary 2 by 1 vector. So if we multiply B by some random vector AB, we end up with this as our first entry and this is our second entry. Okay, so what does this actually mean? Well, notice this is -3 times this. So the only vectors in the span of the columns of B are vectors of the form where they have something, and then the second entry is -3 times that something. So these vectors all lie on a line. If you like, it's the line y equals, where the y coordinate is equal to -3x. Just plot another point here. So x is -1 and y is 3, which will be this point up here. So the line y equals -3x goes through those 2 points. So it's actually the line that goes through here. So any vector in the span of the columns of B will lie on that line. So it's only one-dimensional. It would move all of the vertices of this square onto that line. And so, of course, because all those vertices would lie on this line, a line has area of 0. So the area of the square has been multiplied by 0 and the square has been mapped to a line. That's what happens when you have a matrix with determinant 0. It takes a higher dimensional object, like a square, 2 dimensions, and moves it to a lower dimensional object, in this case a line. It's the same with this matrix down the bottom here, C. It turns out if you were to go through and do row reduction, you would find that there are 2 linearly independent columns, but the third column is just the sum of the first 2 columns. So this one has 2 linearly independent columns, so its columns span 2 dimensions, even though it's a 3 by 3 matrix. So it would also have determinant of 0. So what that means is if you had, say, a cube in 3 dimensions, and you applied C, the linear transformation, to each vertex of that cube, it would map all of those vertices that are in 3 dimensions onto the same 2-dimensional plane. So all of them would lie on the same plane. Now, in 3 dimensions, the physical quantity we're talking about is volume. So that means the volume would be multiplied by 0, because any 2-dimensional object, any 2-dimensional shape, has 0 volume. So that's why whenever we have a matrix that has one or more linearly dependent columns, it must have determinant of 0. Make sure you understand this theorem that I've just put up. It's really important. So the determinant of a matrix is 0 when and only when the columns of that matrix do not form a linearly independent set, i.e. when at least one of them is linearly dependent. So let's actually go ahead and look at finding the determinant of a given matrix. So it turns out that finding the determinant of a 2 by 2 matrix is quite simple. You just multiply together the two elements on the leading diagonal and subtract the product of the two elements off the leading diagonal. So if we have matrix A as 1, 2, 3, 4, the determinant of A is AD 1 times 4 minus BC, which gives us minus 2. Now, when the determinant is negative, that is just to do with the angle between the first two vectors. So this would still double the area of a shape in R2 if you applied the linear transformation induced by A to a two-dimensional shape. The minus part, again, is just about the angles between vectors. Let's look at one more example of a 2 by 2 matrix. So if this is matrix B, the determinant of B will be element A times element D minus element B times C, which is 12 times 1. So this actually has determinant 0, and that's what we'd expect because the second column is a scalar multiple of the first column. So that's for 2 by 2 matrices, but unfortunately it gets quite complicated quite fast as you increase the size. Let's look at 3 by 3 matrices. So to find the determinant of a 3 by 3 matrix, we do what's called cofactor expansion. You expand along any row or any column. Now, just to keep things simple, let's always expand along row 1. So what we do is we take each element along row 1, one after the other, like the first one would be 1. We cross out all the elements in the same row and column as that element, and what we're left with is a sort of a submatrix. So we times 1 by the determinant of this submatrix. Then we do the same for the next element in row 1, which is 3, and then we do it for 4. So the determinant of A will be 1 times, and we take the determinant of the elements that were left, which was 6, 1, minus 4, and 9, okay? Then we do for the second one, so the second element was 3. So if we cross out all the elements in the same row and column, we're left with this matrix minus 2, 1, 0, 9. And then finally, we do the same for the last element, which is 4. So we'll cross out everything in the same row and column as it. So we'll take our 4 and we'll times it by the determinant of what's left. Minus 2, 6, 0, and minus 4. So what you do is you sort of add these up, except every second one is negative. So the first one's positive, the second one's negative, the third one's positive. All right, so the determinant of this matrix here, so it's 1 times the determinant, is just 6 times 9, which is 54, minus 1 times minus 4. Okay, so the determinant of that 2 by 2 matrix is 58. So we subtract 3 times. Now the determinant of this matrix here is AD, which is minus 18, minus 1 times 0. And then the last one, it will be 4 times the determinant of this 2 by 2 matrix is minus 2 times minus 4, A times D, minus B times C, which is just 0. So what we do is put this all together. We get 58 plus 54 plus 32, which gives us 144. So note, it's not that unusual to get a very large determinant, particularly for matrices that are of higher dimensions, like 3 by 3 matrices or 4 by 4 matrices or whatever. So what this means is if I applied the matrix A to the vertices of, say, a cube, it would form a new cube and its volume would be multiplied by 144. So if the original cube had a volume of 2 units cubed, then the new cube will have a volume of 288 units cubed. So that means it would actually make the new shape, the image shape, quite a lot larger. Okay, so there's just one more thing I need to go through. Unfortunately, it's easy. It's how we find the determinant of some special matrices. So finding the determinant of a matrix by hand quickly becomes hard. You know, for 4x4, 5x5, 6x6 matrices, we usually don't even bother doing it by hand. We get computers to do it. I mean, imagine how hard it would be if you had lots of non-zero numbers. You know, for a 4x4, you'd have to take this element and multiply it by the determinant of this 3x3 matrix, which in and of itself would take a while. And then you'd have to take this element and you'd have to multiply it by the determinant of the matrix formed by these elements here, and so on. It would just take forever. But fortunately, if there are a lot of zeros in the matrix, it makes the determinant a lot easier to calculate. So this theorem can help us find the determinant by hand of some larger matrices if they are of a certain type. So if a matrix is triangular, then all you need to do to find the determinant is multiply each of the diagonal elements. So hopefully you see that the first matrix is diagonal, so that means it's both upper and lower triangular. So its determinant will just be the product of the diagonal elements, so 1 times 2 times minus 3 times 5, which will be negative 30. So the determinant of the next matrix can be calculated in the same way because it's lower triangular. There are no non-zero elements above the leading diagonal. Now, because there's a 0 on the leading diagonal, if you multiply all the elements together on the diagonal, you just get 0. So that will be the determinant of this matrix here. But if the matrices are not triangular, if they have a lot of non-zero elements, finding the determinant of a 4x4 or 5x5 matrix can be very, very hard and computationally very expensive. So sometimes what we will try and do is we'll take a matrix here and decompose it, write it as a lower triangular matrix times an upper triangular matrix. So that will be easy because we can find the determinant of this easily and this easily as well. And then we just use the rule that the determinant of the product of matrices is just the product of the determinants. So that is the so-called multiplicative rule of determinants, okay? So finding the determinant of matrix is not easy, particularly for higher dimensions. We don't do it by hand. We need computers, and sometimes even the computers need little tricks to help them calculate the determinant of a matrix. So this is a very important concept going forward. So I hope you've learned what determinants are from this video. This has been the luckiest maths teacher in the world. Have a great day.